Hey guys, today we're going to learn about telescoping series. And in order to do telescoping series, you need to understand summation notation and you also need to know how to create partial fractions. All right, so luckily we know both, so we should be okay today. So number one, let's just start with a recap of partial fraction decomposition. So this one, it's already factored for us. So we can go straight to one of them's going to be a over k plus 2, and one of them's going to be b over k plus 3. And then remember, we're going to kind of like cross multiply to pretend you're getting a common denominator and see what the new numerators would be. So this term would need the k plus 3, and then the b term would need the k plus 2. And since that's our new numerator, it's going to be equal to 1. And now we're trying to find a and b. And remember, you do that by carefully selecting some x, well, in this problem, k values. So off to the side here, let's pick some strategic k values. I'm going to start with -3. So when you plug in -3 for k, we get a times 0 plus b times -1 equals 1. And then these cancel, and it looks like b is going to be -1. All right, and now we're going to find a. And to find a, let's plug in k equals, let's try -2 this time. All right, so if we plug that in, we have a times 1 plus b times 0 equals 1. And then this cancels, and I think you guys would agree that a would equal 1. And now that we have the a and the b, we can write our partial fraction sum, and that is going to be just plugging in a and b here and here. All right, so it's going to be 1 over k plus 2 plus -1 over k plus 3. All right, so those are the partial fractions. Okay, so here's the new type of problem. It says, determine the infinite sum from 1 to infinity of this fraction. And there's kind of two tricks on a problem like this. The first trick is, if it's going to infinity, we can't find the sum. So instead of infinity, we're going to limit it to n. We're going to say, what's the summation from 1 to n? Okay, and n being like a finite number. And then, instead of writing it like this, we're going to write it as the individual partial fractions. All right, so here we go. So here's what we're doing. We're going to find the sum from k equals 1 to n, first of this one, 1 over k plus 2. And then we're going to find the sum from k equals 1 to n again of this partial fraction, -1 over k plus 3. And then let's just list out a couple of terms, and you're going to notice a pattern, and it's going to be called a telescoping series, and you'll see why in a minute. So let's start getting some terms here. When k equals 1, isn't this 1/3? And then when k equals 1 here, you get -1/4. All right, let's just keep going. Let's plug in k equals 2 now. When k equals 2, this is 1/4. And when k equals 2, this is -1/5. Just in case you don't see the pattern yet, let's go one more time. When k equals 3, this is 1/5. And when k equals 3, this is -1/6. And now I think you guys are going to see it. I'm going to go ... and now I'm going to plug in n. Okay, because that's our last number we're going to plug in. So when I plug in n, this is 1 over n plus 2. And when I plug in n here, this is negative 1 over n plus 3. Okay, and then remember all the numbers in between as well. We're just can't do them all. All right, do you guys notice a pattern? Or do you notice any terms canceling? And I'm hoping you guys see these are opposites, so they cancel, and these are opposites, so they cancel. So every term is going to cancel with the next term. So I know we didn't do it, but this negative 1/6 will cancel with the 1/6. And then before this one, there was going to be a negative version of it, so that was going to cancel. And that's called a telescoping series. And you're left with just the first term plus the last term. Those are the ones that are not going to cancel because their consecutive terms are not opposite. Okay, so this telescoping series is actually equal to 1/3 plus negative 1 over n plus 3. But we're not done yet. It wasn't n. Remember in the beginning it was infinity? So now we have to say, as n approaches infinity, what does this actually equal? Okay, so as n gets bigger and bigger, 1/3 is just going to stay 1/3. That's not going to change. But as n gets bigger, as you start plugging bigger and bigger numbers in for n, this fraction is going to approach 0. Because the bigger n gets, as you divide by bigger and bigger numbers, you end up getting closer and closer to 0. And that's something we can revisit in class. So then, 1/3 plus 0, final answer is 1/3. Let's do another one of those. Okay, so example 2. Same idea. If we have a sum from 1 to infinity of a fraction, let's break it up into its partial fractions first. Okay, so these problems are kind of a lot of work. So partial fractions will have a over n plus b over n plus 1. And then remember, you're trying to get like a common denominator, so let's see what the new numerators would be. This term would need the n plus 1, and the b term would need the single n. And since that's the numerator, it's going to be equal to the numerator here, which is 1. And then you guys know the drill. Let's pick some strategic n values off to the side to see what a and b are going to equal. So I'm going to choose n equals negative 1 to start. So when I plug in negative 1 for n, I get a times 0 plus b times negative 1 equals 1. And then these cancel, and we can see that b is going to be equal to negative 1. Okay, great. Now let's plug in another value for n. This time I'm going to plug in 0. So if we plug in 0 for n, we're going to get a times 1 plus b times 0 equals 1. And then this one will cancel, and you guys can see that a equals 1. Oh, I don't know why I wrote so big. Okay, that was a mistake. So now not the final answer, but our partial fractions now, if we plug in the a and the b, it's going to be 1 over n plus negative 1 over n plus 1. Okay, those are our partial fraction sum. Oh, sorry, you can't see that. There you go. Now we have to do the actual problem. And again, since we're going from 1 to infinity, since we can't really do infinity, let's call it capital N, and let's write a separate summation with the two partial fractions going from 1 to n. All right, so the first one is going to be the summation from n equals 1 to capital N of only this one, 1 over n. And then the second one will be the sum from n equals 1 to capital N of this one, negative 1 over n plus 1. And let's do what we did last time. Let's get kind of a list going of all the terms as we start plugging in n's, and then let's see what's going to cancel again if this is another telescoping series. Okay, so let's start with n equals 1. When you plug it in here, you get 1, and when you plug 1 in here, you get negative 1/2. All right, let's keep going. Let's plug in n equals 2. So when n equals 2, this is going to be 1/2, and this is going to be negative 1/3. All right, let's do one more. When you plug in n equals 3, what color didn't I use yet? This is going to be 1/3, and you guessed it, this is going to be negative 1/4. Okay, and then dot, 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 let's stop. Now let's plug in capital N. When you plug in capital N, this is going to be 1 over n, and this is going to be negative 1 over n plus 1. All right, so if you see this pattern here that's continuing, these cancel, this will cancel, the previous one and this one will cancel, and again, you'll be left with the first plus the last. All right, so this is really equal to 1 plus negative 1 over n plus 1. But then, kind of like we did in the last problem, it's not n, it was infinity. So now you have to say, well, as n gets bigger and bigger, as n approaches infinity, this fraction, as n gets bigger, will approach 0. Because the bigger the denominator, the smaller the number will get. It'll approach 0. So actually, this one kind of cancels out, and you're just left with 1. All right, so this is equal to 1. That's the sum of that telescoping series. All right, guys, last one if you're still with me. This one is a log series here. So it says evaluate the sum, and it's a finite sum, so we don't have to worry about that infinity business. But the trick for a log is to expand it. If you have the log of a quotient, let's break it up into the difference, right? You subtract. So this is going to be the sum from n equals 1 to 30 of log of n minus the summation from n equals 1 to 30 of log of n plus 1. And you know what, just to be consistent, I'm just going to put the negative sign on the inside. It doesn't matter. Like adding a negative is the same as subtracting. So remember from, I don't know what chapter it was, when you have the log of a quotient, it's the same as the individual logs being subtracted. All right, just like before, let's start listing some terms. So let's start when n equals 1. This is going to be log 1 plus negative log 1 plus 1 is 2. All right, we're just going to list our terms and see if we see a pattern. Then let's plug in n equals 2. So when you plug in n equals 2, this is going to be log 2 plus negative log 3. All right, if you want to do it one more time, now let's plug in n equals, what are we on, 3. This will be log 3 plus, when you plug in 3, negative log 4. Okay, and then let's do dot, 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 and let's finish off with 30. So if you plug in 30, this is going to be log 30 plus negative log 31. All right, now if you notice that pattern again, a lot of stuff cancels. Negative log 2, negative log 3 log 3, negative log 4 log 4. There would have been a negative log 30 to cancel with the log 30. And again, you're left with log 1 plus negative log 30. So this is equal to log 1 plus negative log 31. I think I might have said 30. I meant 31. But let's clean it up a little. Log of 1 we know is 0, right? So the log of 1 is 0, so the answer is just negative log 31. Okay, that's the sum of that series. All right, I know that was a little wild. I hope it made sense. If not, we will practice it more in class the next day. Thanks for watching.